Hello, in this video we're going to look at the Poisson probability distribution, named for a mathematician whose name was Poisson. The distribution is represented as shown here. We have random variable x distributed. We use PO to represent the Poisson distribution, and a mean is the only parameter we need to represent that distribution. So x here is representing the number of occurrences of a specific event within a fixed time interval, where mu is representing the mean number of occurrences within the interval. Occurrences of the event are random and independent. So this could be, for example, the number of cars that pass by on a particular point, a particular intersection in a 1 hour period, or it could be the number of sales that a shop is making in a day. So these are a specific fixed time interval. We have a mean number of occurrences, but of course, there can be any number of occurrences within that. So this is a discrete probability distribution, like the binomial probability distribution, where we can only have whole number occurrences. And we do have sort of the idea that these occurrences must be random and independent. There's a formula given here. It involves, we can see why it would have to be discrete because our denominator involves factorial, which only really works for whole numbers. And it involves exponential, so e to the power of negative mu times mu to the power of x. What we know about the Poisson distribution is that the expected value, which just is average, is going to be mu. The variance is also going to be mu. That could be shown using the actual formulas. We're not going to bother dealing with that right now. But using that formula is one possibility. The other possibility is that a lot of calculators will have the binomial distribution programmed into it, much like they have the Poisson distribution, much like they have normal and binomial distributions programmed in. And we will have the option then of using a probability distribution or a cumulative probability distribution, depending on what we're doing. So let's take, for example, an auto shop that performs an average of 31 oil changes in a day. So in other words, we have a Poisson distribution. So X is distributed according to Poisson with a mean of 31 in a day. If we change the time interval, that will change the mean. And we want to find the probability that they do exactly 31 oil changes tomorrow. So the probability that X equals 31, according to that formula, is going to be e to the power of negative 31 times 31 to the power of x over, x being 31, mean to the power of that, over 31 factorial. Or in my calculator, depending on the calculator you have, it might look a little different. On the TI, it's called the Poisson PDF, and you can find it in the distribution menu. On the Casio graphing calculators, it's in the stats app, and it's Poisson PD. Either way, you're going to have to put in a couple of things. You're going to have to put in the x value we're looking for, which in this case is 31. And you're going to have to put in the mean, which is actually also 31. And when we do that, we get a probability to 3 significant digits of 0.0715. So about a 7% chance that they'll do exactly 31 oil changes. I'll note here that unlike the probability distribution for binomials, for example, a binomial probability distribution is discrete, but it has a limited number of possible outcomes. If I'm only doing 10 trials, I have a maximum of 10 possible successes, so 0 to 10. Poisson distributions are open-ended. Obviously, the minimum number of occurrences of the event can be 0, so I do need to have whole numbers greater than or equal to 0 as my possibilities, but there's no theoretical upper limit. It's just the probabilities will eventually become vanishingly small. So in theory, according to this distribution, there's not no probability of 1,000 oil changes in a day, despite the actual logistical limitations on this particular auto shop. But statistically speaking, that's going to be essentially 0. Now, if I'm doing something where I'm doing at least 25 oil changes, so the probability that X is greater than or equal to 25, there's no upper limit. So I definitely can't just calculate this by hand. I mean, I could go until I get probabilities that are so basically 0 that I can stop adding them on, depending on what precision I want. But this is actually going to be 1 minus the probability of X being less than 25. And this is where we can use the cumulative distribution feature. But note that for the cumulative distribution feature, I'm going to be using an X value of 24 because I want to include all of the probabilities from 0 to 24. and then I will subtract that from 1. So my X value would be 24. My mean is still 31. And when I do that calculation, I get 0.119 roughly. So the probability when I do 1 minus that is going to be 0.881. Let me just double check that, because subtraction is always the bane of my existence. So yes, that is correct. So they do at least 25 oil changes. That's going to be a much higher probability, about 88%. Now, if we change the day, the time interval, so what's the probability that they will do 180 oil changes next week, Monday to Friday? So this is now 5 days. And we'll assume, because it wasn't stated otherwise, that the 31 oil changes in a day is independent of what day of the week it is. So my new mu is going to have to be 5 times 31, or 155 oil changes in a week. And we just want to know the probability that they'll do 180 oil changes in the week. So 180 oil changes in the week is going to be back to just the Poisson probability distribution, not cumulative, because I have an exact number. But this time my X value is going to be 180 and my average is going to be 155. My mean is 155. This is a very tiny probability. So the probability that X equals 180 in this case is going to be about 0.00438. You can express that in scientific notation. I'm actually going to express it as a percentage, 0.438%. And so that's quite a tiny probability of doing exactly 180, even though that is not wildly outside the realm of realistic in this instance.